Hi everybody, welcome back to grade 12 physics. What we're going to look at today, we're not actually going to introduce any new sort of concepts. What we're going to do is we're going to build on them and look at how we can use what we do know to look at some more complicated problems and some more difficult, more realistic scenarios. And so what we have to help us, keep in mind, are kind of three really big things. So we have Newton's three laws of motion. So we have those we can use. We've got free body diagrams, and we've also got kinematics equations. And the reason why kinematic equations are going to be helpful is that if we have velocities or times or distances, they can actually then help us get acceleration, which we can use in third law, or pardon me, Newton's three laws and free body diagrams to get forces acting and things like that. And just before we move on, one quick definition I want to introduce to you, this idea of equilibrium. If something is in equilibrium, what that means is the sum of all the forces acting on that object are zero. And so what that means is this object is not accelerating. So whenever an object is not accelerating, we can say that it's in equilibrium. Okay, so with that in mind, let's jump right into some of these examples here. So again, we're looking at a little more complicated than we have in the past. So in our first example here, we have a sled hanging on a hill, and we're going to say the hill is very icy, so there's negligible friction. And there's a rope tying it to some pole, and the rope is holding it so it's steady. So the first thing we can notice is that this is in this is in equilibrium. And what that means is, again, is that the sum of the forces have to add to zero. And I want to know two things. I want to know the magnitude of the tension, and I want to know the magnitude of the normal force. So what we're going to do is we're going to start by drawing our free body diagram. So that's this guy right here. We've got three different forces acting on it. We've got the normal force. That's due to the fact that the sled is being pushed up from the ground so it doesn't fall through it. We've got gravity pulling it back into the ground. And we have the tension force from the string pulling it up. And we know all three of these things have to sum together to get zero, since this thing is at rest. But you might notice right away that we're dealing with an angle here and we have some forces that are at angles. So how do we know where these things are pointing? Well, the first thing we know is tension is pointing directly up the hill. And you can see I've drawn it the same sort of direction. Here's the rope, here's the tension. Gravity always points straight down towards the center of the earth. And the normal force, this is where sometimes people get a little confused, is that normal force always points perpendicular to the surfaces that are in contact. And if you've taken math, I don't know what grade exactly it's in, but when you start talking about vectors coming off of planes, so I guess it must be in calculus and vectors, you're going to use the word normal to a vector or normal to a plane. And what that just means is it's a 90-degree angle. So the normal force always comes off of the surface at 90 degrees. And the other thing that's sometimes a little bit confusing is this angle theta that appears in the diagram, how steep the hill is. How did I know that it was here? And so what we can imagine is, well, let's say gravity is straight down. And let's pretend for a second that the hill is flat. So horizontal, flat hill. Where would theta be? Well, it would be zero because the hill would be flat. And what that means is the force of gravity would be the force of gravity would be parallel to the normal force. It would be one straight line through it. And as you're raising up the hill, getting theta bigger and bigger and bigger, this angle in here would be becoming larger and larger and larger. Now there is like an algebraic way to kind of go through this, or geometric way to prove that this angle theta is the same as this angle theta. It's using your C patterns and Z patterns and that sort of stuff. And if that's something you want to see in class, then by all means let me know and I'll show you. But I think I can kind of do a hand waving argument here and say that this theta is the same as this theta. Okay, so what we want to do is we want to, just like we did before, pick a coordinate system. And so normally what we're doing is what's called y straight up, let's call x straight across, and we'll work from there. But sometimes when we're dealing with angles, we want to change that because we want to make the least amount of work for ourselves. And the way we can do that, because if I put the coordinate system right here, I have a force of gravity that's acting straight down, but these two other vectors are acting at an angle. That means I have to break two vectors into the components. But if I do a little bit of forethought here and I rotate this coordinate system, which I can do, there is no real reason why I can't, and put it like this, and I hope what you can see is the normal force is going to be straight up the y-axis, the tension force will be straight up the x-axis, and the only one I have to break into components then is the force of gravity. And I've gone and done that already right there. So there's the force of gravity acting in the y direction. Here's the force of gravity acting in the x direction. And we know, again, what we can say is that since this thing is not accelerating, the sum of the forces here have to be 0. So if we scroll down, I've done a little bit of that already. I've said the sum of the forces in the x direction are 0, and the sum of the forces in the y direction are 0. So our next step then is going to be to write out where are these forces coming from. So we have to think about what's causing these forces, or at least which direction are they pointing. So in the x direction, so that's again this one up here, we have two forces acting. We have the tension force, which is acting in the positive direction. So I can say the force of tension. And I've also got this force here, the component of gravity acting along the same direction, but it's going in the opposite direction. And if this is the positive x direction, we'll subtract the force of gravity then and get that equal to 0. And then over here, we can do the same thing and say, okay, well, the force of the normal, let's try that again. Force of the normal, subtract the force of gravity in the y direction, so that's cos theta, has to be equal to 0. And I just realized here I forgot sine, so let me go ahead and stick that in there, because it's only the component of gravity that's acting in that direction. Sine theta. All right, equals 0. So here's our two F net statements for both our directions here. And let's scroll back up and just see what is our ultimate goal here. So this has asked us to find the magnitude of the tension in the rope. So the only one that has tension is the x direction. So let's deal with the x direction first. And I can rearrange this so it says, the force of tension is equal to the force of gravity. That's awful. Let's try it again. The force of tension is equal to the force of gravity sine theta. And if I do some plugging in here, the force of gravity is mg sine theta, or say theta is 25 degrees. I can get that the tension works out to be 58 newtons. All right, so there's part A done. So I know that the magnitude of the tension force is 58 newtons. And the second part of this question is asking me the magnitude of the normal force acting on the sled. So if I return to the y components here, I actually have an expression with the normal force in it. And I can write this as the normal force is equal to the force of gravity times the cosine of theta. And again, I'll leave that one for you, and that'll be one of the questions I'm going to ask you in the follow-up here. What does this work out to? So that'll be the first question in the little follow-up quiz at the end. All right, so we found the tension force, we found the normal force, so I think that question is finished. We've answered everything. Great, so let's move on then to the next part of the question. So now we've got the same sled, but what's going to happen is we have a coefficient of friction, and we're going to cut the rope. So we're going to take this rope, we're going to slice it, so let this thing slide, and we want to see what's the acceleration going to be. So this is not static equilibrium anymore. We know that because there will be an acceleration. Well, we're assuming there's an acceleration because there's sliding happening. And we're going to do the same thing. We've rotated our coordinate axes, and we've drawn our free body diagram. The difference here is that the force here is not the tension force, it's the force of friction. And we know that because we've cut the rope, so tension is gone. So if we had no friction, this would slide down the hill, and friction opposes motion. So what I've done is I've written the F net statements, or the sum of forces statements, for the x component and the y component. Notice that y still is 0. What that means is the sled is not accelerating into or out of the hill, but the x component is no longer 0. The sum of the forces is negative ma. So pause for a second and think about, why is that a negative value? What would cause this to be negative as opposed to positive? And if you've got an answer, let's move on. It actually has to do with because which way is acceleration happening? The acceleration is going to be happening in the negative x direction because, well, we're going to assume that. So let's assume that this thing accelerates in the negative x direction and work from there. So with that in mind, let's write our forces statement here. So what I've got for this one is that Fk minus Fg sine theta equals negative ma. And for the y component, I have Fn equals Fg, pardon me, Fn minus FG cos theta equals 0. All right, so I've got this, and I want the acceleration. So my ultimate goal is to get an expression for this guy right here. And if I look over here, I know the mass, I know sine theta, I can find the force of gravity, but I don't have the force of kinetic friction. And over here, there's no acceleration. So at first glance, it seems like I'm stuck. It seems like I can't do anything else. But not quite, because there is one connection between these two. And it actually has to do with the force of friction. The one thing, again, we talked about last time, if you remember, is that the force of friction, kinetic friction, is given by, force of kinetic friction is given by mu k Fn. So I actually have an expression here. So let's solve this for Fn. So this one's going to be Fn equals Fg cosine of theta. And I know that Fk is mu k Fn, so I can write this guy, the first, the x component, as mu k Fn, minus, so it's mu k Fn minus Fg sine theta equals negative ma. And again, I know that Fn is equal to Fg cos theta, so I can write this as mu k Fg cosine of theta minus Fg sine theta equals negative ma. Do some rearranging for a, and you should end up with, and let me know again if you have trouble with this rearranging, but you should end up with a equals sine theta minus mu k cosine of theta times g. And I don't like how I wrote that. Let's try that again. So a equals sine theta minus mu k cosine theta times g. All right, that looks a little better. So there is my expression for the acceleration. I have all of those values, and I'm ready to sub some numbers in. So if you sub those numbers in, you plug them in your calculator, I end up with an acceleration. Oh, turn my pen back on. I end up with an acceleration of 3.1 meters per second squared. And I think that makes sense because we know the acceleration is going to be less than g. It's not falling straight down. It also has friction it has to contend with. And so we have an acceleration of 3.1 meters per second squared. But as I like to do, let's take this to the extreme case. So let's first of all pretend that theta is 0. What would that mean? Well, that would mean we're on a flat hill. And if theta is 0, sine of 0 is 0, and cosine of 0 is 1. And so if theta were 0, our acceleration would turn out to be mu k times g. And at first glance, you say, whoa, how does that make sense? Because if this were on flat ground, it wouldn't accelerate at all. But notice we've made a bit of an assumption here. We've assumed that we're dealing with kinetic friction, which means this thing is moving. So what this would actually tell us is the rate that this would slow down. So it would be negative mu k times g. That was how fast the acceleration would be, but in the negative direction, causing this thing to slow down. The other like extreme case would be if theta is 90 degrees. That would be free fall. So we're hoping our acceleration turns out to be g. And I'll leave it to you to verify that it does, but we do end up with the acceleration being equal to g. So that's quite helpful. We know that at least this equation makes sense in our endpoints, so it's probably a good answer to be confident in. All right, so on to our last example then. And what we have here is a little bit more difficult. We have two objects here. We have A and we have B. These two blocks connected towards each other, or connected with each other. And we've done problems like this already, but now we're going to have friction down a ramp. So we've added a couple different complications to it. But for the first go here, we're going to, again, have this thing frictionless. So let's leave friction off for now, just to make our lives a little bit easy. But we still have angles, we have tensions, we have normals, we have gravity. So let's go through our systematic approach again. So the first thing, again, we want to do is set up a coordinate system. And what I'm going to use for my coordinate system to make sure that we're keeping our directionality straight, I'm going to have positive, and I'll draw, let's say, green, positive being in this direction. So anytime if block A goes down, that's a positive acceleration. If block B goes up, that's a positive acceleration. So that's going to be um, my coordinate system. And once we've set up a coordinate system, we draw a free body diagram. Let's look at A's, because A is a little bit simpler to begin with. And so A, we're going to say the force of gravity down is equal to the force of gravity down and the force of tension up are the only forces acting. And the sum of the forces in the A direction, or from on block A, is equal to the mass of A times the acceleration of the system. Again, I've only have one acceleration here because these two blocks are tied together. We don't have to worry about having two accelerations. They will accelerate together. So here's the F net statement for A. And for B, I'm saying the net force, or the sum of the forces on B, is equal to MBA. And so we do need to then think about what direction this thing's going to accelerate. And I think it makes sense that this thing will accelerate, if it's going to, along this plane. So let's call this the axis we're concerned about. And so we're going to say this is our positive direction here. And I'm going to ignore everything in this direction for right now. I hope that's okay, because we don't have any sort of forces. We can say that's going to be normal force is equal to this force here. So this is our angle theta here again. And I can then say that this force here is equal to Fg cos theta. And this one down here will be Fg sine theta. So again, I can write my Newton's second law statements here. So let's start with one for A. So that means, if considering my directionality, I picked to be positive, the force of gravity acting on A minus the force of tension is equal to MAA. And over here, what I can do again is say that the force of tension minus the force of gravity on B times sine theta is equal to MBA. So the masses are different, but the accelerations will be the same. And these tension forces will also be the same. So if you look at this now, hopefully you can see I've got two equations with two unknowns, because I don't know what the tension force is, I don't know what the acceleration is, but it appears in both equations. And I know everything else in the equation. So now it's just a matter of subbing one into the other and doing a little bit of rearranging. And so let's get started on that then. So let's work to begin with on this equation here. So I can write this as Ft equals mga minus ma. Oh, hold on. Sorry, I messed my script over there for a second. So this should be mag, that's better, minus maa. And this one, I can say the force of tension is going to be equal to mba plus mbg sine theta. Just set those two equal to each other, and you should end up with mag minus maa equals mba plus mbg sine theta. All right, so there's our kind of statement there. We have one equation with one unknown now, so it's just a matter of doing some common factoring and some rearranging. And what you should end up with here is we have the acceleration is equal to ma minus mb sine theta over, oh my goodness, I should just write this out. Let's try this again. Sorry. Ma minus mb sine theta over ma plus mb all times g. So again, I'll leave it to you to verify that's what you get. But if you do that, I'm getting the acceleration to be 5.3 meters per second squared, and it's a positive number, which means we were correct in our assertion about which way this was going. It was going this way, so this block A will accelerate down, and block B will accelerate up. There's the acceleration. And part B is to find the tension in the string. And again, I think I've done enough here with you, so I'm going to leave that for an exercise here. That'll be my second question in the little quiz here. So the first, or the two questions I'm going to ask you is, where's the first one here? What is the normal force in this situation? And the other question will be, what is the tension in the string in this example here? Okay, so I think that's that's it out of me for today. If you have any questions, again, be sure to ask me in class, and I'll see everybody in the morning. Have a good night.